Good morning, ma'am. My name is Charanteja. I am from CSC AML A section, second semester. Today, my topic is about higher order homogeneous differential equation. This presentation explores the interaction of higher order homogeneous differential equation, providing a comprehensive overview of their definition, solution techniques, and practical applications. Defining higher order linear homogeneous equations. First, what is a higher order differential equation? Let us know what is a higher order differential equation. A higher order differential equation is an equation involving derivatives of an unknown function where the order of the equation is greater than 1. The order refers to the higher derivative in the equation. For example, if the highest derivative is the second derivative, it's a second order differential equation. A first order differential equation has the form f of y comma dy by dx is equal to 0. A second order differential equation involves the second derivative in form of f of y comma dy by dx comma d square y by dx square is equal to 0. A higher order equation refers to equations where the order is greater than 2, like third, fourth, or even higher derivatives. Homogeneous differential equation. Now coming to homogeneous differential equation. A differential equation is homogeneous if all the terms involve the unknown function and there are no constant terms or terms that are just function of the independent variable like x alone. For example, homogeneous equation for second order: a into d square y by dx square plus b into dy by dx plus cy is equal to 0. Non-homogeneous equation for second order only: a into d square y by dx square plus b into dy by dx plus cy is equal to f of x, where f of x is a non-zero function. For higher order homogeneous equation, differential equation, there are no terms independent of the function y into x. The general form looks like this. This is an example of the equation: an into d power ny by dx power n plus an minus 1 into d power n minus 1 y n1 y by dx power n minus 1 plus so on a1 dy by dx plus a0 y is equal to 0, where the order of the equation is n. Now solving uh, roots and solutions strategies. Real distinct roots, uh, repeated roots, complex roots. These are the roots in the higher order homogeneous equation. Now solving homogeneous differential equation. The most common approach to solve higher order homogeneous differential equation is using the characteristic equation. Here is a step-by-step explanation of this method. Write down these are the step 1. These are the steps uh, for for getting the characteristic equation. For instance, a general second order homogeneous equation is a into d square y by dx square plus b into dy by dx plus cy is equal to 0. Now the second step: assume a solution of the form y is equal to x power rx, sorry, e power rx. There is a common method used by this is a common method used for all for solving linear differential equations where r is a constant of the determinant. Step 3: substitute y is equal to r power, sorry, e power rx into the solution. when we differentiate y is equal to e power rx, we get dy by dx is equal to r e power rx, d square y by dx is equal to r square e power rx. Substitute this into the original equation, e power r square into rx plus br erx plus ce power rx is equal to 0. Factor out e power rx, which is never 0. This is the equation form: e power rx into a ar square plus br plus c is equal to 0. Solving the characteristic equation, we need to solve the above or the equation that we got before. We are left with the characteristic equation: a power r square plus br plus c is equal to 0. This is the final characteristic equation. This is a quadratic equation for r. For higher order equation, you will have a higher degree characteristic equation. Step 5. Find the roots of the characteristic equation. We need to find the roots of the characteristic equations, like two distinct real roots and one repeated real root, and the third one is complex roots. Two distinct real roots. If the characteristic equation has two distinct real roots, say r1 and r2, the general solution is y into x is equal to c1 e power r1x plus c2 e power r2x, one repeated real root. If the characteristic equation has a repeated root, r1 is equal to r2, the general solution is y power y into x is equal to c1 plus c2x into e power r1x. Complex roots. If the characteristics equation has complex roots, r is equal to alpha plus or minus beta I, the solution takes the form y into x is equal to e power alpha x into c1 cos beta x plus c2 sin beta x. General solution for higher order equation. For higher order equations, the process is similar but extends to more roots or repeated roots. For example, a third order equation: a3 into d cube y by dx cube plus a2 into d square y by dx square plus a1 into dy by dx plus a0 y is equal to 0 would have a third degree characteristic equation like a3 r cube plus a2 r2 plus a1 r1 plus a0 a1 r plus a0 is equal to 0. The general solution depends on the nature of the roots for all three roots. Second second order case, we are going to know about second order case also. Let's solve the equation: dx square d square y by dx square minus 3 into dy by dx plus 2y is equal to 0. The characteristic equation of the above equation is r square minus 3r plus r square minus 3r plus 2 is equal to 0. Factor the quadratic r minus 1 into r minus 2 is equal to 0. So the roots are r1 and r2. r1 is equal to 1 and r2 is equal to 2. Thus the general solution is y into x is equal to c1 e power x plus c2 e power 2x, where c1 and c2 are constant determined by initial or bounded conditions. Practical applications. We can apply this in physics, engineering, and other fields. In physics, describing the motion of spring, pendulum, and other physical systems. In engineering, analyzing electrical circuits, mechanical vibration, and control systems. In other fields, modeling population dynamics, chemical reaction, economic growth. Key takeaway and advantages of problem solving. Understanding roots, solving strategies, advanced techniques. Coming to the conclusion, higher order homogeneous differential equations are solved by finding the characteristic equations, determining roots, and forming the general solution based on the nature of the roots. Whether the roots are real, repeated, or complex, the solution method remains similar but extends to include more terms of higher order equation. This method is extremely used for solving linear differential equations and model a variety of physical and engineering and mathematical systems. Thank you.